So a late good morning to the audience and here in this room and on the web. I would also like to really thank the organizers for having asked me to come. I enjoy this meeting tremendously with great discussion. And with that, I need to look how to forward here, there. I have no conflicts of interest. And in the next 20 minutes, I'd like to divide up the talk into 3 parts. First, I'll give you a brief overview about artificial sweeteners and how they convey sweetness. Then I'll talk about association studies. And finally, I'll come to some data and concepts that either refute or support a causal role of artificial sweeteners in the development of obesity. The FDA regulates 6 artificial sweeteners at the present time. The oldest one is saccharin, which is about 300 times sweeter than sucrose. Then we have aspartame, acesulfame, potassium, sucralose, and the latest ones and the sweetest ones are neotame and advantame. In fact, they are so sweet that it's very difficult to deal with them because just a teeny tiny molecule makes everything so sweet and sticks with you. So there is no product yet in which we have advantame, but you will see products in the future. The FDA regulates the accepted daily intake, which means the definition is that you can ingest this amount for your lifetime every day, and you wouldn't see any adverse health consequences. So for example, for saccharin, this is 5 milligrams per kilogram. An easier way to kind of conceptualize this is I express it in sodas. So if you use artificially sweetened sodas, you would drink 3 sodas per day every day of your life, and you shouldn't see any negative health consequences. Also, sucralose is relatively low, so 5 sodas with sucralose, and then you see other ones, acesulfame, potassium, you can drink 30 a day. Hardly anybody will do that, and therefore reach the ADI. There is a publication that came out of South Korea, and that showed, in fact, that children easily reach these ADIs or even go beyond them, especially with sucralose, because of obviously the small body size, and kids, if they drink 2 sodas a day, they may be beyond the ADI. I will not talk in this presentation about stevia. And only because we're very close to Baltimore, I want to bring up briefly the history of saccharin, which doesn't make me proud as a German, and you will hear why. So Konstantin Fahlberg was a Russian who came to Ira Remsen, a wonderful scientist in Baltimore, and asked for a job. And while he was there, worked on coal tar, came home one evening, tired, sat down, had his glass of wine, and it tasted awfully sweet. Tried it again, figured out where the sweetness came from. It came from his fingers. Went back to the lab and figured out it was a product, a coal tar product, which caused the sweetness. And he figured out it is saccharin. So this all happened at Johns Hopkins in 1877. As I said, Fahlberg was Russian. So you need to allow me the parallel the analogy that I want to draw. In Russian, sakkar is sugar, and so he called it saccharin. But if you go and you look at how conserved the word is, you think of conserved DNA that conveys how important certain sequences are for life. And so I'm proposing, despite the bad things we've just heard about sugar, that sugar is something very important, and it's stuck with us throughout Sanskrit to Persian, Arabic, and English. Now, back to science. We sense 5 different tastes. Of course, somebody in the audience will say, well, Christina, how about fat and how about carbonation? But I'm not talking about this today. So I'm sticking to the 5 senses, and people in the audience that have studied this, these senses well in, for example, medical school, they say, but isn't it that you sense sugar in the front of your tongue and sour on the side and so on? So this is out. That's absolutely not true. We have these sensors in our taste buds, and these taste buds are located mostly laterally and posteriorly on the tongue, but in each one of these taste buds you have one cell, and that one cell signals only one taste. Once this cell is activated, for example, here in case of the sweet, bitter, and umami receptors that all share the same structure, namely they're all 7 transmembrane G protein related receptors, then that message goes up via the cranial nerves and goes to the insula and tells the insula what it tasted. So the interesting fact is that taste receptors are actually not only located on the tongue or the oropharynx. Actually, that's also a misconception. You have taste receptors all over your mouth. But they're not only in the mouth. They are actually also, for us, very importantly, in the gut and on the pancreas, on pancreatic, for example, beta cells. What they do in the lungs, we really have no clue. And you can see if you were a fly, you even had them on the tips of your wings, so there are things that we really don't understand yet. But these taste receptors in the intestine, they really fascinate us, and enteroendocrine cells in the intestine, they have these sweet taste receptors. And you all know that if you ingest food, you ingest carbohydrate, you increase your incretin hormones. And in fact, whether you do ingest glucose or any other carbohydrate or you ingest an artificial sweetener makes no difference. You will stimulate these taste receptors. It's sweet. So I'll come back to one of the products of the L cells in the intestine, and this is the cell that makes glucagon-like peptide 1, GLP-1, one of the important incretins. You may know that analogs have been developed that are now being used for diabetes treatment because GLP-1 decreases, slows gastric emptying, decreases appetite, decreases glucagon, and increases insulin. So now let me go to associations. We've heard so much about associations. I'm going to go through it very quickly. It seems like the obesity epidemic has leveled a little bit. When I see this graph, I always want to point out that this is not true for minorities. So African American, Hispanic populations, it doesn't look like this. This is the total assessment in the United States. Now, this is this association thing. Just like the obesity epidemic developed, we introduced artificial sweeteners one after the other. And in an audience different from this one, I took the slide out. I like to say, well, you know, associations, the exactly same curve is bottled water use in the United States. And you see this increase in obesity, bottled water. But bottled water, what is it in? It's in plastic, right? So in this audience, I will not say that this isn't a good example. So, but I want to mention in my eyes, qualitatively very interesting study, good study, that was published in 2008 by Sharon Fowler. She asked the question, artificially sweetened beverage use and long-term weight gain fueling the obesity epidemic. And she looked at a large cohort, namely the San Antonio Heart Study. This is a study of more than 2,000 people. It is mostly white Americans and Hispanic Americans. And what they did is they assessed at the very baseline, when they enrolled the participants, they assessed their food intake. And they asked the smart question, how much soda do you drink? And do you drink diet soda or regular soda, and so on? So this is what this is based on. Then they follow the people prospectively. And what I'm showing you here in these bars is the change of BMI after 7 to 8 years follow-up. So we all gain a little weight as we age, at least until age 60, 70, then maybe it goes down again. But I'll give you an example what these bars mean. So let's say my height, 5'6", a little heavier, 155 pounds, my BMI is 25. So I am expected, if I don't drink, that's the first bar, none, if I don't drink any diet soda, to gain over 7 to 8 years a little bit, so that my BMI actually goes up by 1, so then I'm at 26. And that means I would have gained 6 pounds, half a pound a year. Many of us are lucky if they drink. So now let me drink 1 soda a week. So we're going to the third bar. If I drink one diet soda a day, this is between 3 and 10 a week, I'm expected to end up at 26.5. Well, for me, this is hardly noticeable. But on a population basis, this is very important. So now let me come to more causality-related things. And I want to go from the Petri dish to animal studies and then address different populations. So starting with the in vitro studies, in different cell lines, so either pre-adipocytes, 3T3L1 cells, mature adipocytes, or taken human mesenchymal stem cells, you do see increase in adipogenesis. So you can actually drive pre-adipocytes into adipocytes faster by adding acesulfame, potassium, saccharin, sucralose. In mature adipocytes, you see that there is decreased lipolysis. You see more lipid accumulating. And in our own data, which will also be presented at the Endocrine Society later this week, we show that in human mesenchymal stem cells, you have decreased lipolysis. We have heard yesterday in Barbara Corky's beautiful presentation that various artificial sweeteners increase insulin secretion from pancreatic beta cells, from rodent cells, and that has also been shown in Min6 cells. The dentists have been happy about artificial sweeteners for a long time. In fact, I like to ask my patients, do you use any artificial sweeteners? And many people, especially the smart students at the NIH, they go, oh, no, they're bad. So I said, well, did you brush your teeth this morning? Oh, of course. Well, then you were just exposed to artificial sweeteners. We all are exposed to artificial sweeteners all the time. You put this lip balm on your lips, it's artificial sweetener. You brush your teeth, it's artificial sweetener. You take your medicine, it's artificial sweetener. So we associate it with diet soda, but it's in many other products, of course. And the dentists are happy about artificial sweeteners in toothpaste because artificial sweeteners are bacteriostatic. And that has been known for a long time. I'm saying bacteriostatic, it just inhibits growth. It's not that it kills the bacteria, it inhibits growth. My colleague Susan Schiffman has also published in 2008 that, in fact, artificial sweeteners, and she focuses on sucralose, suppress the intestinal microflora. This came way before last year's big Nature paper. But I don't know that it got so much attention. The Nature paper, beautiful work by Aaron Elinoff from Israel, that was published last year in September, in a very articulate way, showed us that artificial sweeteners do change the microbiome. I don't want to go into too much detail of his work, but basically, and also because I was a little saddened to see that Another colleague of ours in a community of artificial sweetener related studies, investigators, this is Susie Swithers from Indianapolis, wasn't even mentioned in this paper, though what Elina showed was that if you feed mice with saccharin, they get fat. And you can't even exactly say why they get fatter than glucose-fed animals. He showed that there was no difference in energy intake or energy expenditure. They were just fatter. And ultimately, he deduces the results that it's the microbiome that makes these mice fat, in that you become more efficient. And certain pathways in the microbiome are upregulated that help you use calories that you ingest. A very intriguing study. This is all mice. What was also shown in his study, beautifully done, is you feed mice either with saccharin or with glucose. Then you take their microbiome and put this microbiome into germ-free mice. And these mice look like the ones from whom you transplanted, which means their glucoses eventually are higher and they become fatter. Now, you all know that clinical trials are underway in Sweden, for example, to use human microbe transplantation for treatment of obesity. So we'll see what the human studies show. The data in Elina's paper that I don't think are so convincing, other than showing that the microbiome looks different in people who ingest artificial sweeteners versus the one, I don't think that's too surprising. There is a difference. I don't think there was any causality established in this paper. It just shows they're different. And in fact, when you look at these 381 non-diabetic individuals, and they divided them up into non-consumers and high artificial sweetener consumers, then you could see, for example, that their hemoglobin A1C was a little higher. Also, their BMI was a little higher. Everything is a little worse. But, you know, just think, people who drink a lot of diet soda, what else is different? So I think we need to really go beyond association. Let me come to some interesting animal studies now. Acesulfame potassium, for example, that really struck me as a pediatrician. Lactating rats concentrate acesulfame potassium 6-fold in breast milk. What about humans? Well, we have preliminary studies, and we looked at breast milk, and we also found higher acesulfame potassium concentrations in human milk compared to the serum concentrations in mothers. So I think we will be able, when we do cleaner studies, we'll be able to show that acesulfame potassium also accumulates in human breast milk. Do you say, so what? You have a little acesulfame potassium in there? Well, I don't know what in humans, but we know from these rat studies that the offspring that was exposed during pregnancy and lactation had a higher sweet preference later in life, whether it was caloric or non-caloric. So what I'm saying is we should look in children whether exposure during pregnancy and early life changes their food preference. So now coming to some randomized acute intervention studies with artificial sweeteners. What we have done, basically we were bored because we're trying to recruit kids with type 2 diabetes and they don't want to come. So we're sitting there, we're reading the paper, and we're saying, we saw something interesting in rat studies and said, oh, you know, if this happens in kids with type 2 diabetes and artificial sweeteners, that would be bad. Let's test it. So we gave the kids, before they come and do their oral glucose tolerance test, we gave them a diet soda versus a carbonate, just mineral water. And lo and behold, we saw stimulation of GLP-1, more stimulation of GLP-1 when you give them, pre-treat them with a diet soda. So then we said, okay, now these were the normal kids, take the type 1 diabetes kids. Well, you see the same thing here. The red line is the line that shows you the diet soda exposure, and the blue one is water. So more GLP-1. This was clearly statistically significant. We published it. And that sounds like it's a good thing, isn't it? Because GLP-1, I just told you before, decreases gastric emptying and so on. So, well, great. Maybe that means you should have your diet soda and eat your pizza, and you will eat less pizza because the satiety comes in earlier. In fact, some nutraceuticals have been started to be developed that mix all kinds of artificial sweeteners and based on the principle that maybe you can get your GLP-1 up. But there was the publication by Janina Pepino. She comes from Sam Klein's group. She studied 17 women. These women were mostly black and they were heavy, BMI 42. And she showed that when you expose them to sucralose before you do the oral glucose tolerance test on the, is this a pointer? No, that's the pointer. Here on this side you see glucose levels in red, of course the sucralose pre-exposure, and here you see the insulin levels. So giving these women sucralose before the oral glucose tolerance test made their results worse. So we went back and now we took older, there was 31 adults, older, not older, they are now middle-aged. They're a little heavier than our first group. We went back and we did the same thing. And I'm going to show you results that compare the difference between this AUC, area under the curve, after the exposure to sweeteners versus water. I think that makes a lot of sense. And this is the result. So here you see percent change of insulin, AUC. So the area under the curve was 20% higher when you pre-treated with various diet sodas or artificial sweeteners alone. Now the problem is when you do oral glucose tolerance test, there's a lot of variability. So it's very hard. We need a really large cohort to show statistical significance. We could show statistical significance, for example, with peak insulin, but I must say, now of course we produce the data, I'm not unbiased, but 20% increase, that's as much increase as you get with metformin or with weight loss or with all kinds of things. I feel that this is a clinically relevant difference. So this is acute. What about long-term? And we have very few long-term studies. 2 of them were published back-to-back New England Journal 2 years ago, and they were randomized trials of sugar-sweetened beverage in adolescents, and the other one was in younger children. So let me go to the first one. Beautiful study. These are our colleagues in Boston. And what they did is they delivered to overweight and obese adolescents who habitually consumed sugar-sweetened beverages, non-caloric drinks. So only the ones who drank soda anyway, they now got home delivery of diet sodas, and the other ones got supermarket gift cards with no instructions. You could buy what they wanted to. And then they looked at, if you avoid the sugar-sweetened beverages, you replace them, you make it easy for them, what happens? The first intervention lasted 1 year, and then there was an additional year of follow-up. Problem, yeah, there was a little less weight gain. They were already obese. So there was further weight gain even with the artificial sweeteners at home. And then after 2 years, there was no difference. Okay, so that unfortunately didn't work. The other study, I really like this one here, 641 kids. This was done in the Netherlands. They only took kids who already used sodas. And then they divided them up and they gave these previously soda drinking kids, either they continued to drink soda 1 can a day, or they gave them a artificial sweetener, sweetened drink. And then they looked 18 months later what that did to these kids. And very briefly, you know, all kids need to gain weight. Of course, there was weight gain, and so we need to express it as z-scores. So these kids started around 0 BMI z-score. They're normal weight kids. And then 18 months later, you see that the sugar-sweetened group with the black dots gained more weight than the kids that got the artificial sweetener. Now, that's not too surprising. The problem is this study did not contain a water condition. So you should stay with your BMI Z-score right there, right? So we know now that if you drink soda, you gain weight beyond what you should gain, and if you replace it with artificial sweeteners, you gain less weight. And I want to end this talk with mentioning that our brains are perfectly capable of sensing sweetness and differentiating the sweetness, whether this comes with caloric sweetness or non-caloric sweetness. So here I'm showing work from Frank that was published in 2008. And what you see lightening up, here's our insula that says, hey, there is nice sweetness that came, and it shows whether you sweeten with sucralose or sucrose, you see the same activation. The only thing is certain other areas, and these are dopamine-dependent areas, do not light up when you use artificial sweeteners. So the question is, do we sense different reward when we get sweetness with calories versus sweetness without calories? And of course the question, do we keep seeking for the reward if we only get 2 minutes? I got the reward of 2 more minutes now. But I'm on my last slide, and just wanted to say, I think there is no convincing evidence that artificial sweeteners prevent or alleviate obesity. That's a statement that one can make. I am also convinced that we can show clear-cut data that support that artificial sweeteners in vitro lead to more adipogenesis and less lipolysis, increase insulin secretion, and there I'm now very sure based on our own results. And the question with reward is a very difficult one to answer, especially with regard to chronic use, but needs to be investigated further. Now, we will keep going in our studies and looking at the issue of artificial sweeteners in breast milk. And I think a very important one is the entire research that focuses on microbiome. The only problem is there. In animals, we can establish some causality. In humans, this is extremely difficult. But I think that Elinaf has clearly established in that Nature paper that our microbiome changes with artificial sweetener exposure, and we can distinguish between users and non-users. But does that make us gain weight? I think we're far away from an answer there. And with that, I would like to thank the audience and thank my collaborators and colleagues.
I want to thank you so much for a wonderful presentation, not only of your own research, but also of an entire body of work that's really emerging in this area. And we do have a few questions for clarification.
Yeah,
first question.
Yeah, very nice presentation. Thank you. I wondered if there's a dose response, because this is one of the issues that we've had. We did most of our studies at a dose that I'm not sure is achieved in vivo. And I know the Israeli study was done at an even much, much higher dose. So I wonder if you have any comments to make on dose.
So I think there we need to distinguish between the studies that are done, the in vitro studies, so our own mesenchymal stem cell studies are done with higher doses than you would see in humans after exposure, reasonable exposure to artificial sweeteners, reasonable exposure, let's say 2 cans of diet soda. However, I think the biological effects, so for example, the stimulation of L cells producing GLP-1 and the stimulation of insulin, which I don't know whether it's GLP-1 dependent or whether it's independent, which means that artificial sweeteners go directly to sweet taste receptors on beta cells. Probably both, right? There, I think we have the proofs in the pudding. We expose them, and there is the biological response. But the in vitro studies is a different thing, and so our plan is, and we're just writing also a grant, that we will get down to physiologic doses. So this is very important. However, when you read the Nature paper, in fact, they do say that at least the exposure of the rats, the studies that were done feeding the rats were done with saccharin concentrations that are 5 milligrams per kilogram. So they translated directly the ADI from humans into mice and gave mice a dose that is acceptable in humans.
So one question I have is when we talk about what humans are being exposed to, like with soda, I think we dramatically underestimate. I think many people who drink diet sodas drink many more than 1 or 2 or 3 8-ounce can equivalents a day. I think there are many people who drink 42 ounces several times a day. So I think that we need to be aware that there's a wide range in levels of exposure, and that things that may seem high may, in fact, at least for a segment of the population, not be high at all.
So if I may add something there, this was a summer student project, but I live in an area right around the NIH with a lot of bright people going shopping. And so we set up a little table in front of our grocery store, and we asked people whether they would answer some questions. Only parents who had children be between the age of 1 and 18. And we said, look, here are some products. First we want to ask you a question, and then you choose some products, you do some sham shopping, and then you get actually a $20 coupon and you can go into the grocery store. And the question was, would you give artificial sweeteners to your children? And no, that's bad. And then we asked them to choose the products, and they chose a lot of products that said no sugar added. Well, you can imagine it's exactly the products that contain artificial sweeteners because they have fewer calories. And so even very highly educated people that pick up a yogurt and read the label, and there's acesulfame potassium, ask how many. In the beginning of this research, I didn't know what the difference between sucralose and sucrose is. It just so, I don't think this is something that the population knows about, even very educated people. And so in fact, by trying to avoid certain things, namely calories, you actually pick the artificially sweetened ones, which you didn't want in the first place either. So there's quite a confusion out there.
Thank you. I'm going to now ask the speakers to come forward for a discussion, including those who are online.